we want to show that n follows a Poisson distribution lambda t if it is a Poisson process. So essentially what we're trying to show is that p and t equals k follows the probability density function of a Poisson distribution, but we're replacing our lambdas and x with lambda t and k. So essentially it's going to look like this. So all we've done here is we're using a normal probability density function of the Poisson distribution, and we're just replacing those values with lambda t up here and with k, and that's that. So then we're going to use these three properties to basically show this, and we're also going to use information from our notes. So first I'm just going to define some terms. So n, just number of events, t is time at a given event. So when I mean tk, time at k, and if we have a little t, that is, the value of the time. And then we also have a, and this is kind of an inter-event period. And in the notation, a1 is between the start of our time, so between t equals 0 and the time at our first event, and it's that time period in between those. So we can show that Tn is the time at event n, which is the sum of all inter time periods. So we're looking at a1 plus a2 plus a3 and so on, all the way up till an minus 1 and an. And the sum of that is the time at event n. And so what we're going to be doing is trying to extrapolate that and come out with something really nice. So we're given this, which I will copy and put down here, and we want to use these hints. So I think the second hint is actually the best place to start, because we want to get this this first term nt equals k in terms of tk and then in terms of a, so that we can then use this third rule and use our gamma distribution, which is also in our notes, to work that out. So we're going to use the second hint because we're given that nt greater than or equal to k equals tk less than or equal to t. So nt equals k is found within here, as well as nt is greater than k. So we essentially, to get this term, want to do nt greater than or equal to k minus nt greater than k to then produce nt equals k. Now, to do that, what we want to do, so we can already replace this first term with tk less than or equal to t. So we'll say that is equal to tk less than or equal to t. So what this is saying is that at event k, say we have a value of time t, the time that event k occurs is within is before than or equal to the time. So we then want to make sure that any event n that is greater than k, so we can maybe say, let's say k plus 1. So we want to make sure that the time of the next event k plus 1, which is less than or equal to t, and we want to do that, and that is therefore equal to k. So the reason that happens, so we can imagine like a timeline. Say we have time that when k happens, time that k plus 1 happens, and this is t. So let's say, we randomly drop t here. The probability that this value t is going to be greater than or equal to tk is greater than the probability that it's going to be greater than or equal to k plus 1, because event k happens before k plus 1, before k plus 2, and what we're essentially saying is that if we only really need to consider k plus 1, because k plus 2, k plus 3, they're all the way far into the future, and if k plus 1 doesn't occur, then neither can anything higher than that. So that's all we really need to consider. So I hope that explains that. So we'll just get rid of this. So we have that, and then we know that this is equal to that, so we'll get that in terms of a. So we're saying that the sum of k I equals 1 of ai is less than or equal to t, which is this first section. Now, the second section is just going to be the sum of k plus 1, I equals 1 of ai is less than or equal to t, equals nt equals k. So we can, we know using this that the sum of such are distributed using a gamma distribution. Now our gamma distribution is found on our notes, and so we're basically saying that the gamma distribution of k given t minus the gamma distribution of k plus 1t is equal to this. So if we're doing like the probability distributions of those, in fact, I'll start that again. So these are distributed giving the gamma distribution. So the only thing that's different about them is the k. So we can say that we can have two. So we can say that t of k is distributed with a gamma distribution of k lambda, and t of k plus 1 is also distributed with k plus 1 and lambda. Now, formula is given, so the function of a normal gamma distribution of x, which uses alpha and lambda, given both alpha and lambda are greater than 0, and we are also given that lambda is greater than 0 because we know that t is greater than or equal to 0, and if it's a Poisson process, then we know that lambda has to be greater than 0 anyway. So let's carry on. So the function of that is lambda alpha x alpha minus 1 e to the minus lambda x over, now in my formula booklet it says gamma alpha. Now the gamma function is essentially alpha minus 1 factorial, I believe. Let me check. Yeah, it is. So then we're also given so we essentially want to work out the integral from 0 to t, because we're working in terms of t up here, using our, let's say our tk of lambda k, I think, is that t? Yeah, t k minus 1 e minus lambda t over k minus 1. Or let's just not make it confusing. Let's use x instead, actually. And we'll do this in terms of x minus the integral of zero to t of lambda k plus 1. Change that to x. Change the wrong thing. And this is k plus 1 minus 1, which is k. So we can leave that. E minus lambda x over k factorial dx. Now the formula booklet also includes the cumulative distribution terms of sums. So it says that f of x, which is equal to the cumulative distribution function, 1 minus the sum of n minus 1, it uses j equals 0, e of minus lambda x j over j factorial. So let's try using the sum way first, and we'll see where we get. So we'll do it for, so we're working out p of tk, that's equal to t minus p of tk plus 1 equal to t. We're going to replace our n with k and k plus 1, and we're going to replace our x with t. So this is then going to be 1 minus the sum of k, so this is going to be then k minus 1. We'll keep this with j equals 0 of e to the minus lambda t of lambda t j over j factorial minus 1 minus, now this is k because k plus 1 minus 1 equals 0, j equals 0. E minus lambda t j over j factorial. So let's then, we can cancel out our 1, and this is going to be a plus, and we'll get rid of that, and let's rearrange this as the sum from k, j equals 0, e to the minus lambda tj over j factorial minus e to the minus lambda t, oh, my apologies, minus the sum of k minus 1, j equals 0, e to the minus lambda tj over j factorial. Now, the only difference between these two is that we have k minus 1 here and k. So by taking away the second term from the first term, we essentially only have j equals k, because we're taking away j equals 0 from j equals 0, j equals 1 from j equals 1, you know, continuing up till k minus 1, so that the only term that we're actually left with in each sum, well, in the first sum, is j equals k, which is then e to the minus lambda t k over k factorial. Now, if we scroll all the way to the top, we now have our final result, that the probability of nt is equal to k is equal to e to the minus lambda tk over k factorial. Done. And this is problem 2.4. So we've basically extrapolated these terms, these separate distributions, and shown that nt is distributed with a Poisson distribution. And yeah, brilliant.